Okay. Hi guys, good morning. Shall we start?
Morning, sleep.
Right. So we have been seeing chemical kinetics, correct? Right. So I think last class we saw zeroth order equations and first order equations, isn't it? Right. So we did problems like we saw equations for zeroth order. I asked you to remember two equations for each of them, right? For zeroth order, two equations. For first order, two equations, right? So one is for the equation of the zeroth order, another is for the t half of the zeroth order, right? And again, same for that is the equation of the first order and the t half of the second order. Sorry, first order, right? So we'll do more problems on this. We did enough problems on zeroth order. First order is little important. We'll do more problems on this. Okay. Okay, the question, take it down. For a first order reaction, A giving products. Right, for a first order reaction, A giving products. The concentration of A changes from 0.1 m to 0.025 m. The concentration of A changes from 0.1 m to 0.025 m in 40 minutes, 40 minutes. Right? The question is, find the rate of the reaction. Find the rate of the reaction when the concentration of A. Find the rate of the reaction when the concentration of A is 0.01 m. Right? Find the rate of the reaction when the concentration of A is 0.01 m. Right? Okay, so they're not asking you anything else. They're asking you the rate of the reaction, not the rate constant, or say not the time, not anything else. They're asking about the rate of the reaction. So let me see. I'll give you 2 minutes. You try this question, and let me see if you can bring in the answer. Yes, any answers? Again, if you're smart enough, you will observe something there. So without even doing any calculations, can you tell me what will be the T half of this reaction? Guys, without doing any calculation, can you tell me what will be the half-life period of this reaction?
Minutes.
Yes, good. Right? So it's very simple. Look at this. They are telling that the concentration is changing from 0.1 m to 0.025 m in 40 minutes, isn't it? So look at this. If I have 0.1 m, after one t half, it would have become 0.5, and after another t half, it would have become 0.025. Right? That's what is given here. 0.1 to 0.025. Correct. So they're telling two t halves. 2 into t half is basically 40 minutes. So basically, obviously, t half will be 20 minutes. Right? Now that's it. You got the answer, I guess. Or else, if you're not able, if you're not finding it like this, right, you have to, what do you have to do? You have to go for the first order equation, 2.303 by t into log of r naught by r. All this thing you have to substitute and then get the k value. Now I can directly get the k value because I know my t half. So I know the equation. T half is 0.693 divided by k. Right? So I know t half. I'll be able to find the k value. Right? And then what I have to do? How will I find the rate after I find k? Rate when the concentration is this much. What will I do? How will I do? How will I find the rate?
R into
Are you understanding what I'm
concentration to
telling?
the power of n. I mean K into concentration to the power n.
That's it, right? It's a first order equation. So I have to use my rate law. Isn't it? What does rate law says? R, that is the rate, is equal to K into concentration of A power 1 because it's a first order equation. Right? So A's concentration is given, that is 0.01 m, right? And K just now we found out using the T half. Substitute it there, find the rate and tell me the answer quickly. Yes, answer. So from here I can say that K value would be 0.693 divided by 20, right? T half is 20 minutes. So do it as 10, 0, 3, 4, 6, right? So it will be 0.0346, right? So this would have been my K, 0.034 would have been my K value, and the substituted there. So R will be 0.034 into the concentration of A, which is 0.01, so it's 10 power minus 2. So I can write it as, so totally already I have a 10 power minus 3, or I'll write it properly. So it is 0.034 into 10 to the power minus 2, right? Or I can write it as 3.4 into 10 to the power minus 4 mole per liter per minute, right? The unit here, right? The unit here is mole per liter per minute, because we found T half in terms of minutes, right? So obviously it will be mole per liter per minute. So this is the answer. Anybody got this? Hello. Today something happened, isn't it? Everybody is silent. What happened? Everybody is feeling sleepy, huh? Okay. Right. One more question. Guys, please wake up and solve this problem. I hope everybody understood. Okay, at least just give me a yes if everybody understood this. That you can do, or for that also you're so sleepy.
Yes, sir.
I'm still waiting for yes. Only one guy said yes. Okay, I think today. Cool. Right. Next question. So this is the last question we'll solve today, and then we'll go on to the next topic. Right. So the next question. A first order reaction takes 40 minutes. A first order reaction takes 40 minutes for 30% decomposition. A first order reaction takes 40 minutes for 30% decomposition, right? They're asking what is the T half of the reaction? What is the T half of this reaction? Okay, can you do this?
Sir, can you repeat the question, sir? I couldn't hear you properly.
Yeah, sure. So a first order reaction takes 40 minutes, 40 minutes for 30% completion, for 30% decomposition, whatever it is. 30% completion or 30% decomposition. Now they're asking, find the T half for this reaction.
Okay, sir. Thank you, sir.
Yeah. Quickly do it. I told you how to work with percentages in the first order equation, right? So use the logic, or you can use the formula. So I think then there'll be some log calculations. Right.
So what is log of 1 by 7? 10 by 7.
Nice. Okay. Fine. So let me give you some insights about log. Like I know you're allowed to use log books, right? But you can save some time, right, with whatever I'm going to tell you, right? So you start with log 1. Log 1 is 0. We all know that, right? Okay. Now log 2, you have to remember the value, which is 0.3010. Okay. And log 3 is 0.45 something. Okay. And log 4, you can easily calculate. If I know log 2, log 4, how can I write? I can write it as 2 log 2 because it's log 2 squared, right? So this will be 0.6020, right? Now log 5 would be around 0.7 approximately. I think it would be 0.69 to be exact. Okay. And log 6, how will I be able to write? Log 6, I can write it as log of 2 into 3. Right. So I can write it as log 2 plus log 3. So log 2 is 0.3010. Log 3 is 0.45. So 0.3 plus 0.45 will become 0.75. So log 6 will become approximately 0.75. Right. And log 7 will be 0.83. Log 7 will not be able to write anyway. And log 8, how can I write? 3 log 2, right? 3 log 2 will be 0.9, right? And log 9, I'll be able to write it as log, okay, 2 log 3. Log 3 value is 0.45. Okay, so this is okay. Basically, you can see that log 8 is also this thing, so it's actually 0.88 something. Your log 8 value, and 3 log 2 will become exactly 0.9, and log 10 value is 1. Right. So in this, what and all value which you have to remember, right? You have to remember log 2. You have to remember log 3, log 5, log 7. That's it. So if you can remember all these 4 values alone, right, all the other things are going to become easy. Okay, so you don't have to every time check the log books, right? So here, even in what is your electrochemistry, you will use log values so much, isn't it? So it's better to remember like this, right? And it is going to help for your competitive exams also, right? Okay, answers? Just 1 second, I think there's a glare coming. Just give me a moment. I'll try the problem.
The time in minutes itself, everything.
Yeah, time in minutes itself you can keep. No problem.
So then I get the answer as 70 minutes, like 71.
70 minutes approximately. Okay, we'll check. Okay, I think everybody has taken this down. Okay, so I have the equation goes like this. So first I have to, okay, they're asking me t half. So for finding t half, I need to find k first, right? So k can be found from the equation 2.303 by t. T is 40 minutes log of r naught by r. Now they are given 30% decomposition or 30% completion, right? Say if I keep R naught as say R naught itself, right? Now the final concentration means, like final concentration is, they say the 30% is over. So how much is remaining? 70% is remaining.
70%.
Isn't it? So I can write it as 0.7 into R naught. Right? 30% completed. So the final concentration of the reactant would be 70% of the initial concentration. Right? So it's done. Right? So it would be 2.303 divided by 40 into log of 1 by 0.7 is there. Or I can write it as a log of
Log 10 minus log 7.
Minus log 7. I'll be able to write it like this. Okay, so log 10 value is 1. So it'll be 1 minus, now only we saw what was log 7's value. Log 7's value was around how much?
0.83.
Okay, 0.83. Okay, so it will be 0.17. So 2.303 into 40 will become into 0.17. Now this is my K value, right? So now for finding T half is 0.693 divided by K, right? So now let me take it to there. So this first column I will drop, right? So it will be T half would be 0.693 divided by 2.303 into 0.17 into 40. Okay, this is actually a very big calculation, right? So guys, if you can remember one thing, how did you get the 0.693? That's actually going to help. You got 0.693 from this log 2 into 2.0303 is what is my 0.693. This is how you got 0.693. Correct, right? So basically log 2 into, so log 2 value is 0.3010, right? So now I'll be, if I write this as 0.3010 into into 2.303. So this and this gets cancelled. Done. Right? So 2.303 got cancelled. Okay, so what I have is 0.3, or if I approximately do it, 0.3 into 40 will become 12 divided by 0.17. Correct? Right? So 12 divided by 0.17. And that calculation should be a little easy. Right? So if I write it as,
I saw that log 7 is equal to 0.84, sir. Maybe
no
that
problem,
might affect. Is that okay? Because if we...
no problem. But yeah, actually, if you're doing it for your school, it's very, very required that exact values are taken. But here, like if at all in case log values are not given, you can manage. That's why I gave you the values.
Okay, sir.
It doesn't matter. Fine. So 1200 divided by 17. One time. Oh no. Okay. So it is 17. Say if I put it as 7 times 9, 4, 11. So it should be definitely okay. This is the thing. So 7 times 119 10. So done. So I don't have anything.
We need to put 0, point, and then continue, sir.
Okay. Yeah.
70 point something.
Yeah, 70. So it will be 100. So I think it should be 70.6
5.
or 70.5. Yeah, the answer is 70.5 mole per liter. Per liter.
Per liter per minute.
Oh, sorry, it's minutes, right? Okay, it's minutes. 70.5 minutes. This would have been the answer. Approximately, again, we did a lot of approximations. You should not do this, right? Just for conserving time, I did this. Okay, so 70.5 minutes would have been the answer. Yes, the answer is correct enough. Right. So yeah. So hope you understood. It's very simple formulas, 4 formulas, 0th order and 1st order. If you can remember, 5 marks or it's at least 4 marks from your boards is solid. Done. And obviously, given that, you'll do your calculations properly. Okay, fine. So we'll move on to the next topic. Right, shall we? Okay, fine. Now, you tell me, right? So we saw so much about rates and all that, right? Can you come up with what are all the factors, right? What are all the factors which can affect the rate of a reaction?
Catalyst,
Good. Catalyst, yes. Then
temperature also.
temperature
Pressure.
also, yes.
Pressure.
Pressure to some, if it's a gaseous reactants, yes, true. Okay, then
Concentration.
Concentration, sir.
yes, yes, yes. Concentration of the reactant matters, yes. Okay, then one last. The nature of the reactants, right? For example, if I put sodium in water, it is going to react very fast. If I put iron in water, or say magnesium in water, that is going to be slower. So again, it depends on the nature of the reactant also, right? So yes, all the factors which you told me are the correct way. Like these are the ones which are going to affect the rate of the reaction. And among them, we saw if I have the concentration, one of the things you told me is concentration. We saw if at all the concentration changes, right? How the rates are varying. We saw, isn't it, in terms of first order, second order, or even when we found out the order of the reaction, right? So we saw how if concentration varies, the rate of the reaction is varying. That we saw, right? So we are going to go for the next two things. That is when I go for temperature or when I go for a catalyst, right? How is my rate varying, or say how is my rate constant varying, is what we are going to see now, right? Okay, so we are going to see the effect of, first we'll take temperature, effect of temperature on K. K is rate constant. Okay, fine. For us to understand this, right? For us to understand this, we really have to know how a chemical reaction happens, right? How a chemical reaction happens. Okay, so actually this will be a separate topic in your NCRT, and again, whatever I'm going to tell you now will be a separate topic, but you will be able to connect them both. Okay, so we will see one thing now. We are going to see something called as collision theory. Okay, we are going to see something called as collision theory. Okay, so what this theory explains how a chemical reaction happens, basically, right? This collision theory explains how a chemical reaction happens. Okay, so as the name tells you, right? So we are going to speak about collisions, right? We are going to speak about collisions, right? Okay, so now what it says is that the reactant molecules which are there in the reaction mixture, right? They are going to undergo continuous collisions among them, right? They are going to undergo continuous collisions among them, right? So that they will be able to form a product. That's what it says, right? In collision theory says that the reactant molecules are going to undergo continuous collisions among themselves, right? And they are going to form the product. It is very simple words, right? Fine. So if you actually look into what are the inside details, right? Okay, so let me say that I have two reactant molecules, right? Two reactant molecules are there, right? And say they're going to come together, they're going to come closer and undergo the collision, right? They're going to come together and undergo collision, right? So when they undergo the collision, before the reaction got over, right? In between the reaction, you will see that there is going to be some substance like this getting formed, right? So this, I am going to call it as an intermediate, right? This, I'm going to call it as an intermediate. Okay. Now, instead of calling it an intermediate, if I want to give a technical term, right, some good term to this, I will be even calling it as an activated complex, right? This is my transition state. Like before, these two are the reactants. They're coming together and they're going in between the reaction. There will be something called as an intermediate. It is also called as an activated complex. Right? Now, this activated complex will do something and changes itself into the products. Right? This activated complex will do something. Right? So it will either actually gain something or lose something. Like actually, you can get these things from the organic chemistry part. You know what are intermediates, right? So you know how intermediates eventually will form the products, isn't it? Say they will accept H plus or they will lose the nucleophile. Something will happen. There are so many ways by which I'll be able to convert an intermediate into a product, right? So something will happen, right? And that this intermediate or the activated complex will eventually form products. Okay, this is what my collision theory says. Very simple, right? Reactant molecules are going to undergo collision. They first will form the activated complex, and the activated complex will lose something or gain something, or it will do anything to form the products. Very simple, right? But there are certain conditions in this, right? What conditions? Now, say not all collisions. So you can see there'll be millions and millions of collisions happening between the reactant molecules, isn't it? Right? There'll be so many number of collisions, but not all of them. But not all of them will end up in product formation, right? But not all of them will end up in product formation, right? So the collisions have to have certain factors which has to be satisfied, right? So that collision becomes a successful collision. What do you mean by successful collision? The collision will end up in a product. That's what you mean by a successful collision, right? So for a collision to be successful, right? For a collision to be successful, there are certain criteria which has to be satisfied. Okay, so we'll see what are all the criteria. Okay, so this is a very simple picture. You hope you understand what is happening here, right? So we are going to see, right? We are going to see the conditions for successful collision. Right? Conditions for successful collision. Okay, so the first condition, right? The first condition is the energy factor, right? So the thing is, the reactant molecules, when they are undergoing collision, should have some minimum amount of energy, right? Should have some minimum amount of energy, right? Only if they have that much amount of energy and if they undergo the collision, that might end up in the product, right? So the first thing is, I should have some threshold energy. Threshold means what? Minimum energy, right? So I need to have some threshold energy possessed by the reactant molecules in order for it to form the activated complex, or say eventually the products, right? So this is the first factor, right? Some minimum energy must be possessed. If the reactant molecules' energy is lesser than the minimum value, even though if they collide, it is not going to form the products. Okay, right? So this is the first factor. That should energy consideration. The first is that I should have some minimum energy, right? Second is that yeah.
So that threshold energy, it will vary for different complexes, sir.
Definitely. It will vary for different reactants, different reactions. Yes.
On what factor will this energy depend on, sir? Like the nature of the reactants or the conditions?
Yeah, it is going to depend upon the nature of the reactant as well as the mechanism of the reaction. Like how do I put it? Say for example, say if I have carbocation, take organic chemistry is the best example I can take, right? Say if I assume that it is all going to depend upon what kind of activated complex or what kind of intermediate to form in the reaction. Okay, so if the intermediate is little stable, right, so that particular energy concentration can be little less because stability and energy are inversely related, right? But if the activated complex or the intermediate formed is very, like I said, it's very unstable, then I have to supply, then this energy will be very, very high. So it depends on three things, I would say. One is the nature of the reactant, definitely. And second thing is it is going to depend on temperature for sure, right? The threshold energy is definitely going to depend on temperature. And third thing, it is going to depend upon the mechanism of the reaction. Mechanism in the sense what kind of intermediates are getting formed in the reaction. All these things, these three things matters for this energy to be considered. Understood?
Yes.
Right? Cool. So yeah, so they should possess some minimum energy. I understand. Okay. So next thing is that they should have proper orientation of the basically. Okay. The thing is they should have proper orientation when they undergo collision. Okay. How do we understand this? Right. Fine. Let me take an example. Right. Okay. So now I'm going to have NO plus ozone molecule is going to form NO2 plus O2. This is the reaction. Okay. NO plus O3 gives NO2 plus O2. Simple reaction. Okay. Fine. Now, how does orientation in the sense like whether they can collide like this or they can collide like this, lot of like they can collide like this, any type of collision is possible, right? But there should be proper orientation, like they should be properly collide so that the product formation will happen, right? Now, how do I visualize this in this reaction? Is very simple, right? Now, if you look at NO is going to look like this, right? And O3, hope you know how it looks. One single bond and one double bond, right? And obviously in NO2, you know how it's going to look. This is our two double bonds with oxygen. Okay. So please keep this in mind because this all matters, right? The structures which I wrote here matters there, right? Okay. So we'll see what happens. Okay. So what are you trying to see, right? What are you trying to see here is that one of the oxygen atoms from ozone, right? One of the oxygen atom from ozone is attacking the nitrogen. Is it not? One of the oxygen atom from ozone, right, is attacking the nitrogen molecule and it is forming a bond. Isn't it? Right? And what? Okay, there are two oxygen atoms. The middle oxygen atom cannot be actually, what to say, the middle oxygen atom which is here will not be able to take part in the reaction. It is either going to be either of the terminal oxygen atoms from the ozone. Either this oxygen atom or this oxygen atom should collide with nitrogen, right? So that it is going to form NO2. But again, which is more favorable? This oxygen atom or this oxygen atom? Definitely this oxygen atom is more favorable. Why? Because it is only a single bond which can be easily broken, and you can see in O2 the double bond stays. Right? In O2, if this particular thing is completely there in the form of O2. Right? So two things you have to understand. You have to understand that one of the oxygen atoms from the ozone is attacking the nitrogen atom, right? And there are two oxygen atoms which are possible. Out of them, the first one, that is the one which is having a single bond with other oxygen atom, will only attack the nitrogen molecule. Correct? Right? So only if the orientation is such a way, whatever I told you in that way, if it is there, then it can go for the product formation. What I'm trying to tell you is that if I have an orientation like this, N and O, single bond, O, double bond, O, now this collision will give me product. Say if I have some other collision like this, say N, O, O double bond, O, like it doesn't make sense, right? I already have an oxygen and the oxygen molecule from the double bond is colliding. No, this will not give me any product. Say one more, I can tell you, say N double bond O. Say now this collision again doesn't make sense. The middle oxygen atom is colliding with the nitrogen atom, again doesn't make sense. So this two doesn't make sense, but this, yes. So now you understood what do you mean by proper orientation when they undergo collision. Okay. Right. So these two are the conditions which has to be satisfied. Right. That's what collision. This is all about collision theory. Collision theory says that reactant molecules are going to undergo collision, so they'll form an activated complex, and that activated complex will gain something or lose something to form the final products. And the collisions has to follow two conditions. One is that they should have threshold energy, and there should be proper orientation of the reactant molecules when they undergo collision. That's all about collision theory. Right. So why did I teach collision theory? Is because I want you to understand the concept of this threshold energy, right? Because that's what you're going to see now. Like I told you, this threshold energy is actually going to depend upon the temperature, right? And the reactant molecules' properties, and say so many other things. Even catalyst actually decides the threshold energy. So we'll see how exactly it goes, right? So hope you have understood what is collision theory and the concept of this minimum energy which must be possessed. Okay, cool. So we'll move on, right? Okay, so generally what happens, right? Generally what happens when I increase, so we are saying all this to understand how the rate or the rate constant will vary if I change the temperature, isn't it? That's what we are trying to see here, effect of temperature on K, right? Now generally, like from the collision theory, what you can understand is, right, from the collision theory what you can understand is, if I increase temperature, right, if I increase temperature, right, can I say the frequency of collision? I assume that before the temperature was 25 degrees Celsius, right, the temperature was 25 degrees Celsius, and the number of collisions happening per minute, right, number of collisions happening per minute between the reactant molecules was say 100, right? There were 100 collisions happening per minute between the reactant molecules when the temperature was 25 degrees Celsius. Okay, now what I do is I increase the temperature. I make the temperature to be 50 degrees Celsius. Okay, now I make the temperature to be 50 degrees Celsius. Now what happened there? Basically, when I increase the temperature, I increase the amount of energy I supply to those particular molecules. So their energy will increase, right? Their energy will increase. And obviously, the number of times they undergo collision, that is the frequency at which the collision is happening, would have got increased. So before it was 25 degrees Celsius, the number of collisions per minute was around 100. Now it would have gone around to 200 or 300 collisions per minute because the temperature got increased, right? So whenever you increase temperature, the frequency of collision increases, as well as what does it increases? The energy possessed by the reactant molecules are also increasing. Okay, so now from all this, what can I say? If the energy is increasing, if the number of collisions or say the collision frequency is increasing, definitely the reaction is going to become faster. That's what I understood, right? The reaction is going to become more and more and more faster if temperature is increased, right? This is the general case again, right? Okay, this is, so generally what they say is that if temperature is increased by some 10 degrees Celsius, right? If temperature is increased by 10 degrees Celsius, say 25 to 35, right? This is a very general statement I'm telling, right? This is very general, right? So if the temperature is increased by 10 degrees Celsius, they say the rate almost doubles, right? So this is a thing they say, general statement, but again, this cannot work for every way, like every case it will not work. Generally they say that if temperature is increased, right, the rate doubles. That's what they say. Okay, but we will be able to get a proper mathematical relationship, right? We will be able to get a proper mathematical relationship between your rate constant and your temperature, the rate constant and your temperature. Okay, so for us to go through that, right, for us to go through that, I'll first directly give you the equation, right? So this is a very, very important equation. It is called as Arrhenius equation, right? This equation which I'm going to see is what is called as Arrhenius equation, which is actually going to connect, right? It's actually going to connect the rate constant with temperature. Okay, there is actually a derivation for this, but the derivation is a little complex. It is out of the scope of 12th. If you go to college, maybe you'll study. But now I'm going to directly give you the equation, right? The equation goes like this: K, that is the rate constant, is equal to A e power minus EA by RT. This is an equation which you have to remember, right? K is equal to A into exponential of minus EA by RT. Okay, so I know K is the rate constant, right? And this A is what is called as Arrhenius factor or Arrhenius constant. That will be given in the question. Again, that depends on different reaction, right? If the reaction changes, my A value changes, right? And T is the temperature. You can see this T is my temperature, right? R is the gas constant, and since you're using, since you're using energies here, right, I'll tell you where the energy comes. So this EA which I'm writing here is what is called as activation energy. We'll speak about it more, right? Since you're using energy values in terms of joules, right, you have to use the R value as 8.314 if you want the answer in terms of joules. Okay, you have to use the R value as 8.314. Universal gas constant R value is 8.314 if you want the answer in terms of joules. Okay, and sometimes, very rarely, they can even ask the question they want the answer in terms of calories. That is also a unit of energy, just like joules, right? So if R value is asked in terms of calories, R value is 2 in terms of calories, CAL. But again, 99.99% they might not ask you, right? So anyway, so it's just it's easy to remember the values. 8.314 in terms of joules and 2 in terms of calories. These are the R values. Okay, and this EA which I have here, right? This EA is what is called as activation energy. This EA is what is called as activation energy. Okay, so the equation is K is equal to A e power minus, they say this e power has this whole term, E minus EA by RT. This whole thing is in the power. Okay, so this EA is what is called as activation energy. Okay, sir, I understood almost everything except for EA. I completely understand, right? So what do you mean by this activation energy? Okay, now the thing is, guys, right? So let me go back to collision theory. Okay, let me go back to collision theory, right? Now assume that that particular molecule, they say there are going to be so many collisions. Initially, when talking about the initial stages of the reaction, right? When I just start the reaction, right? The reactant molecules will undergo collision. I understand, but most of the reactant molecules will not have enough energy, right? Most of the reactant molecules will not have enough energy, but they will gain some energy as they undergo more and more collision. Is it not? Say they initially they will come very slowly and go back, but in the second collision they can come back and go like this. Are you able to get what I'm saying, right? So the first ever collision, first few collisions are always it is not successful, right? So it will take some time for the reactant molecules to gain enough energy through the collisions for the collisions to become successful. Are you able to get what I'm saying, right? So initially the reactant molecules will not have enough energy. They will gain more and more energy as they undergo more and more collisions. Okay, and then they will reach a peak. Then the minimum value is reached, right? Then after the minimum value is reached, then only the product formation starts, right? So this minimum value which I'm talking about is what is my activation energy, or in proper words, you saw the intermediate in the collision theory, the activated complex, right? The energy possessed by the activated complex is what is my activation energy, right? The energy possessed by the activated complex is what is called as my activation energy. Okay, so I can give you a proper definition. Please take down for activation energy. Right, you ready? Right. So it is the energy barrier. Activation energy is the energy barrier which has to be crossed. Activation energy is the energy barrier which has to be crossed in order to form activated complex, in order to form activated complex, and eventually the products. Okay, so activation energy is the energy barrier which has to be crossed by the reactant molecules to form the activated complex, and obviously from the activated complex I go for product formation. That's what I said. Okay, what is the time? Okay, we have time. Cool. So now, hope you can understand the gist of it, right? What is activation energy? So basically, some energy has to be increased for the reactants so that it forms the activated complex. And this activated complex is highly unstable because it has so much energy. So from the activated complex, the energy will be released so that the product formation starts. That's how it's going to be. Okay. So if you can visualize the same thing, whatever I wrote here in the form of a graph, right? You will be able to understand. You'll be able to get more insight about what is this. Okay, we'll look into it. We are going to see the graph for this activation energy. Okay, fine. So the graph is right. So here I have the reaction coordinates. Reaction coordinate in the sense it is going to talk about whether reactants are there or products are there. It doesn't have any physical sense. Okay, I'll explain you. Don't worry. Right? Reaction coordinate in the sense from reactants to products. That's what it is. There is not a number. Okay, fine. Now in this I have the potential energy. Okay, and this entire diagram is what is called as the energy profile of the reaction. Right? This entire diagram is what is called as energy profile of the reaction. Okay, cool. Now this is how the graph is going to look for almost any of the chemical reaction. I would not any of the chemical reaction. Fine. So we'll be able to do this. So for a simple elementary chemical reaction, you know what is an elementary chemical reaction? It is going to finish in single step reaction. Right? Okay. So this is how it's going to look. Say initially the potential energy, we're talking about the reactants here. So initially the potential energy of the reactant, the energy possessed by the reactants are not enough, right? So what will they do? They will undergo more and more collisions, right? They will undergo more and more collisions. So their energy value will keep on increasing, right? The energy value will keep on increasing. Okay. Now at a point of time, they would have had minimum energy. They would have had the required energy, and that required energy would have been possessed by the activated complex. So you will see this energy will keeping on increasing, and it is going to attain some saturation. And this particular point where I have the maximum energy reached, right? So this is where the activated complex is formed, right? And obviously the energy possessed by the activated complex is what is my activation energy. Okay, and obviously what happens after that? After the activated complex is formed, done. Now the product formation can go into the picture, right? Now the product formation starts. How the product formation will start? Definitely you can see that the activated complex is having very high energy, right? So the energy has to get decreased. How the energy will be decreased? By losing energy, right? So the energy will be completely keeping on getting lost so that the product formation will start. So you will see that I attain a peak, and you will see that the product formation is there, right? So you can even, okay, so this is how the graph looks. So you can see that the energy is keeping on decreasing, right? So here the product formation has started. So this saturation curve indicates that the product is completely formed. The reaction is over, right? This saturated line indicates that the reaction has gotten over. Okay, so you can see from the activated complex, the energy keeps on decreasing, and then you'll eventually form the product completely, and the reaction has gotten over, right? Now, why did I call it as an energy barrier? Now you can see initially the amount of the energy possessed by the reactant is very less, right? Now due to number of collisions increasing, you saw that this energy barrier, right? This energy barrier has to be crossed. That's why I'm gonna call it as activation energy as the energy barrier, which has to be crossed by the reactant molecules to form the activated complex and eventually to form the products. Okay, so now I'll be able to give you one more thing. So if I draw a dotted line here, right, at the dotted line, at the exact middle point, it is the activated complex. That is understood, right? So left of this point, that is this side of this point, this entire region, right, talks about the reactants, right? And after the activated complex is formed, I would say this region, right, talks about the products. So now you can understand what do you mean by reaction coordinates, right? The reactants to products formation. That is just indicated here. Okay, so energy profile diagrams will give lot of insights about the reaction. I will be able to tell from the energy profile diagram how many intermediates are there, whether the reaction is going to happen in a single step or whether it's going to have multiple steps. That can be understood from the energy profile diagram. And one more thing I'll be able to understand is whether the reaction is exothermic or endothermic. That also will be able to understand from the energy profile diagram, right? So all that we'll see next class. How and all we'll be able to use the energy profile diagram is very, very, very important, right? So hope you have understood the concept of how activation energy will actually play a role, right? So if this energy barrier is very, very big, what can you tell about the rate of the reaction?
Slow.
Right, it will be a slower reaction, isn't it? Obviously, right? So I would say the activation energy and the rate are inversely related. If I have very high amount of activation energy, right? So the rate will be very, 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 very slow. It will be a very slow reaction, right? So in that case, I'll be going for catalyst. So we'll see how catalyst, now from the energy profile diagram, I will be able to explain you how catalysts are able to increase the pace of the reaction. That also can be told. Okay, so all these insights, all these interesting things we'll see next class, right? Until then, we'll see. Take care. Bye bye. Yeah, doubt?
Sir, why P of reactant is more than P of product, sir?
That's a very good question. So you can understand that this particular case, right? It explains the endothermic reaction. It explains the endothermic reaction. If it's an exothermic reaction, you will see ulta. The reactant molecules would have had higher energy than the product molecules. That's what I told you. One of the things we'll be able to find out from the energy profile diagram is whether the reaction is exothermic or endothermic. We'll see next class. It's actually a very nice question.
Okay, sir.
Okay, understood?
Yes, sir.
Cool. Any other doubts, guys?
So,
Okay. Yes, Kanna. Yes, any doubts?
sir, I said no.
Okay, fine. Cool then. We'll see, guys. Again, I think next Tuesday. We'll see. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah.